Hi, my name is Dylan Evans, and today I'll be researching and comparing the models that Ontario has used to model COVID-19 infection rates, keeping in mind the concepts we have learned and discovered from the beginning of the course, such as intervals, domain and range, and asymptotes. Before looking into COVID models, we must first grasp our understanding of the two basic models we are looking for, one being the exponential function and two being the logarithmic function. First, we have the exponential function, which can be used to model rapid growth and rapid decline of COVID cases. The base exponential function is 2 to the power of x, has a horizontal asymptote of y equals 0, which means if we want the model to eventually eliminate COVID, this function can never reach 0. Here is an exponential growth graph of COVID-19. With this graph, some issues come into play, including the model assumes that cases are either decreasing or increasing at an exponential rate, which doesn't line up with the real world all the time as nature is sporadic, which means it's better used to get a general estimate of case numbers rather than a real accurate number. An exponential growth rate also was made evident around the world at the beginning of the pandemic in many countries and would signal a rapid growth in cases. In this case, a global lockdown is needed. The second model we can use to graph COVID is a logarithmic function. They are different to exponential functions as they increase much slower than exponential functions. This is what you want the curve to look like, essentially controlled with the lockdown. There are a few things that have to be taken into account when designing a logarithmic growth model for COVID cases. Firstly, restrictions would have to be placed on the range so that the function does not go below 0, as there is no such thing as negative COVID cases. Secondly, is a vertical asymptote that x equals 0. And so, if you wanted to connect this model to existing data and use it as a projection for the future, and vertical horizontal translations may be needed, as well as restrictions to the domain and the range of the logarithmic projections. Also remember to take into account that since logarithmic functions is the inverse of exponential functions and the domain of logarithmic functions is the range of exponential functions and vice versa, in general, the function y equals log bx, where x is greater than 0 and b cannot equal 1, is a continuous and one-to-one function. Therefore, this model is better for long periods of time when compared to the exponential growth model, as it is much better at showing accurate averages. We can analyze these models and try to understand the benefits or downfalls of the lockdowns. In this graph, Ontario's cases increases was projected around 3 to 5% growth, projecting us to have around 5,000 cases a day. Fast forward to December 19, and experts realized projections which stated that 7% growth rate in cases and no lockdowns. This was modeled using an exponential function. Then by the 24th of January, we would have around 28,000 cases per day. Then we see the province of Ontario went into lockdown on December 26, 2020. The aim of the lockdown was to achieve a decline in the cases. What ended up happening was that the graph went from an exponential growth to an exponential decline, beginning around 2.5 weeks after the lockdown went into effect. You can look back at the comparison between the December 19 projections and what actually happened in this graph right here. It has defied even the experts' predictions, as January 12th, the Science Table released new projections which predicted that the case numbers would continue to rise under the current restrictions at the time. Here's the graph of the case numbers from the middle of November until the end of February. As you can see, the lockdown has played a huge impact in the cases, reducing our daily case number by around 75%. Between the period of early January and the end of February, proving the effectiveness again of the lockdown. Thank you for listening and goodbye.